The Global Positioning System, GPS, is a satellite constellation supporting highly accurate positioning, navigation and timing, (PNT), measurements worldwide. As one of the first satellite positioning systems, GPS has become integral to work done worldwide, including precision agriculture, autonomous vehicles, marine or aerial surveying and defense applications. GPS is one of many GNSS, global navigation satellite systems, that provides positioning, navigation and timing, (PNT), measurements. While operated by the U.S. Space Force, a branch of the U.S. Armed Forces, GPS is available for use by anyone worldwide. GPS was started in 1973, launching its first satellite in 1978. Satellites are developed and launched in series known as blocks. In total, 10 Block I GPS satellites were launched between 1978 and 1981. The Block II series satellites were launched beginning in 1989 and were capable of broadcasting on 2 L-band radio frequencies. GPS Block II had several developmental series, including Block IIA, IIR, IIRM, and IIF. Each set of satellites built upon the previous designs and capabilities, culminating in Block III. This third generation of GPS satellites begins with Block 3A series new signals and higher broadcasting power. The first 3A satellite of 10 was launched in 2018. GPS stands for Global Positioning System. It's also often used to describe the positioning system itself, for example, your vehicle's built-in GPS. GPS includes 3 main segments: the space segment, control segment, and user segment. The GPS space segment includes over 30 satellites in orbit operated and maintained by the U.S. Space Force. These satellites broadcast radio signals to control and monitoring stations on Earth and directly to users requiring highly precise satellite positioning. The U.S. Space Force also oversees the GPS control segment. It includes master control and backup control stations, dedicated ground antennas and several monitor stations located worldwide. These stations work to ensure GPS satellites are healthy, orbiting in the correct locations and have accurate atomic clocks on board. These stations are integral to the overall health and accuracy of the GPS constellation. The user segment includes everyone relying upon GPS satellites for PNT measurements. From a mobile phone providing directions to autonomous vehicles requiring lane-level positioning accuracy, from a farmer tracking planting and harvesting routes year over year to a UAV mapping a rainforest, many applications use GPS for high-precision positioning and accuracy around the world. Satellites are continually broadcasting their orbital position and exact time at that position on radio frequencies. That signal is received by antennas, along with at least 3 other satellite signals, and then processed in a GPS receiver to compute a user's location. GPS broadcasts on L1, L2, and L5 civilian frequencies. GPS also broadcasts on L3 and L4 for governmental and regional satellite-based augmentation systems, SBAS. Several satellites also broadcast M-code, a military code carried on the L1 and L2 frequencies designed for exclusive use by the U.S. military. A positioning system is only as good as its processor. A high-precision GPS receiver will be far more accurate than a mobile phone, for example. Potential sources of errors are identified and modeled at monitoring and control stations to optimize accuracy. Most errors come from clock errors, orbital drift, atmospheric and multipath delays and radio frequency interference. These sources constantly threaten positioning, navigation and timing accuracy by contributing to geometric dilution of precision. Some technologies help mitigate dilution of precision and these errors, including subscriptions to GNSS/GPS correction services, SBAS, and the fusion of additional sensors like inertial navigation systems or radar. More precise GPS receivers also help mitigate errors through different algorithms by computing a position through pseudo-orange or carrier wave calculations. GPS supports applications around the world relying on satellite technology for assured positioning, navigation and timing measurements. These applications differ by industry, but the use of GPS is based on their need for a precise position, reliable and safe navigation, tracking and monitoring an object's movement, surveying and mapping of an area, or timing within a billionth of a second. For example, mining applications rely on GPS to survey an area before beginning operations. Companies track potential mineral deposits, identify which areas to avoid to lessen their environmental impact, and enable autonomous machinery transporting minerals across the site. Applications requiring high-precision positioning use GPS alongside other constellations. However, because of its encrypted M-code signal, the U.S. military relies on GPS in a unique way. M-code enables the military to secure continual access to positioning and build resiliency to potential jamming and interference sources. GPS equipment enables the accurate PNT measurements necessary in solutions and applications across many industries. From defense to mining, agriculture to commercial marine, GPS is required for reliable positioning, safe navigation and highly precise timing. The Global Positioning System, GPS, is a satellite-based radio navigation system owned by the United States government and operated by the United States Space Force. It is one of the global navigation satellite systems, GNSS, that provide geolocation and time information to a GPS receiver anywhere on or near the Earth where there is an unobstructed line of sight to 4 or more GPS satellites. It does not require the user to transmit any data, and operates independently of any telephonic or internet reception, though these technologies can enhance the usefulness of the GPS positioning information. It provides critical positioning capabilities to military, civil, and commercial users around the world. Although the United States government created, controls and maintains the GPS system, it is freely accessible to anyone with a GPS receiver. The GPS project was started by the U.S. Department of Defense in 1973. The first prototype spacecraft was launched in 1978 and the full constellation of 24 satellites became operational in 1993. Originally limited to use by the United States military, civilian use was allowed from the 1980s following an executive order from President Ronald Reagan after the Korean Airlines Flight 007 disaster. Advances in technology and new demands on the existing system have now led to efforts to modernize the GPS and implement the next generation of GPS Block 3A satellites and Next Generation Operational Control System, OCX, which was authorized by the U.S. Congress in 2000. From the early 1990s, GPS positional accuracy was degraded by the United States government using a technology called selective availability, which could selectively degrade or deny access to the system at any time, as happened to the Indian military in 1999 during the Kargil War. As a result, several non-US entities including Russia, China, India, Japan, and the European Union have developed or are developing their own global or regional satellite navigation systems. Selective availability was discontinued on May 1, 2000, in accordance with a bill signed into law by President Bill Clinton. When selective availability was discontinued, GPS was accurate to about 5 meters, 16 feet. GPS receivers that use the L5 band have much higher accuracy of 30 centimeters, 12 in, while those for high-end applications such as engineering and land surveying are accurate to within 2 centimeters, 3-4 in, and can even provide sub-millimeter accuracy with long-term measurements. Consumer devices such as smartphones can be accurate to 4.9 meters 16 feet or better when used with assistive services like Wi-Fi positioning. As of July 2023, 18 GPS satellites broadcast L5 signals, which are considered pre-operational prior to being broadcast by a full complement of 24 satellites in 2027. The GPS project was launched in the United States in 1973 to overcome the limitations of previous navigation systems, combining ideas from several predecessors, including classified engineering design studies from the 1960s. The U.S. Department of Defense developed the system, which originally used 24 satellites, for use by the United States military, and became fully operational in 1995. Civilian use was allowed from the 1980s. Many civilian applications use one or more of GPS's three basic components: absolute location, relative movement, and time transfer. Amateur radio, clock synchronization required for several digital modes such as FT8, FT4, and JS8, also used with APRS for position reporting, is often critical during emergency and disaster communications support. Atmosphere, studying the troposphere delays, recovery of the water vapor content, and ionosphere delays, recovery of the number of free electrons. Recovery of Earth surface displacements due to the atmospheric pressure loading. Astronomy, both positional and clock synchronization data is used in astrometry and celestial mechanics and precise orbit determination. GPS is also used in both amateur astronomy with small telescopes as well as by professional observatories for finding extrasolar planets. Automated vehicle, applying location and routes for cars and trucks to function without a human driver. Cartography, both civilian and military cartographers use GPS extensively. Cellular telephony, clock synchronization enables time transfer, which is critical for synchronizing its spreading codes with other base stations to facilitate intercell handoff and support hybrid GPS/cellular position detection for mobile emergency calls and other applications. The first handsets with integrated GPS launched in the late 1990s. The U.S. Federal Communications Commission, FCC, mandated the feature in either the handset or in the towers, for use in triangulation, in 2002 so emergency services could locate 911 callers. Third-party software developers later gained access to GPS APIs from Nextel upon launch, followed by Sprint in 2006, and Verizon soon thereafter. Clock synchronization, the accuracy of GPS time signals, plus or minus 10 ns, is second only to the atomic clocks they are based on, and is used in applications such as GPS-disciplined oscillators. Disaster relief/emergency services, many emergency services depend upon GPS for location and timing capabilities. GPS-equipped radiosondes and dropsondes measure and calculate the atmospheric pressure, wind speed, and direction up to 27 kilometers (89,000 feet) from the Earth's surface. Radio occultation for weather and atmospheric science applications. Fleet tracking, used to identify, locate, and maintain contact reports with one or more fleet vehicles in real time. Geodesy, determination of Earth orientation parameters including the daily and subdaily polar motion, and length of day variabilities, Earth center of mass, geocenter motion, and low degree gravity field parameters. Geofencing, vehicle tracking systems, person tracking systems, and pet tracking systems use GPS to locate devices that are attached to or carried by a person, vehicle, or pet. The application can provide continuous tracking and send notifications if the target leaves a designated, or fenced-in, area. Geotagging, applies location coordinates to digital objects such as photographs, in EXIF data, and other documents for purposes such as creating map overlays with devices like Nikon GP1. GPS aircraft tracking. GPS for mining, the use of RTK GPS has significantly improved several mining operations such as drilling, shoveling, vehicle tracking, and surveying. RTK GPS provides centimeter-level positioning accuracy. GPS data mining, it is possible to aggregate GPS data from multiple users to understand movement patterns, common trajectories, and interesting locations. GPS tours, location determines what content to display, for instance, information about an approaching point of interest. Mental health, tracking mental health functioning and sociability. Navigation, navigators value digitally precise velocity and orientation measurements, as well as precise positions in real time with the support of orbit and clock corrections. Orbit determination of low-orbiting satellites with GPS receiver installed on board, such as GOCE, GRACE, JASON-1, JASON-2, TerraSAR-X, Tandem-X, CHAMP, Sentinel-3, and some CubeSats, example CubeETH. Phasor measurements. GPS enables highly accurate timestamping of power system measurements, making it possible to compute phasors. Recreation, for example, geocaching, geodashing, GPS drawing, waymarking, and other kinds of location-based mobile games such as Pokémon Go. Reference frames, realization and densification of the terrestrial reference frames in the framework of Global Geodetic Observing System. Co-location in space between satellite laser ranging and microwave observations for deriving global geodetic parameters. Robotics, self-navigating, autonomous robots using GPS sensors, which calculate latitude, longitude, time, speed, and heading. Sport, used in football and rugby for the control and analysis of the training load. Surveying, surveyors use absolute locations to make maps and determine property boundaries. Tectonics, GPS enables direct fault motion measurement of earthquakes. Between earthquakes, GPS can be used to measure crustal motion and deformation to estimate seismic strain buildup for creating seismic hazard maps. Telematics, GPS technology integrated with computers and mobile communications technology in automotive navigation systems. In military, GPS applications include navigation. Soldiers use GPS to find objectives, even in the dark or in unfamiliar territory, and to coordinate troop and supply movement. In the United States Armed Forces, commanders use the commander's digital assistant and lower ranks use the soldier digital assistant. Frequency hopping radio clock coordination, military radio systems using frequency hopping modes, such as SYNCARS and HAVQUIC, require all radios within a network to have the same time input to their internal clocks, +/-4 seconds in the case of SYNCARS, to be on the correct frequency at a given time. Military GPS receivers, such as the Precision Lightweight GPS Receiver, PLGR, and Defense Advanced GPS Receiver, DAGR, are used by radio operators within a radio network to properly input an accurate time to said radio's internal clock. More modern military radios have internal GPS receivers that synchronize the internal clock automatically. Target tracking. Various military weapons systems use GPS to track potential ground and air targets before flagging them as hostile. These weapons systems pass target coordinates to precision-guided munitions to allow them to engage targets accurately. Military aircraft, particularly in air-to-ground roles, use GPS to find targets. Missile and projectile guidance. GPS allows accurate targeting of various military weapons including ICBMs, cruise missiles, precision-guided munitions, and artillery shells. Embedded GPS receivers able to withstand accelerations of 12,000 g or about 118 km/s, 260,000 mph/s, have been developed for use in 155 mm, 6.1 in, howitzer shells. Search and rescue. Reconnaissance, patrol movement can be managed more closely. GPS satellites carry a set of nuclear detonation detectors consisting of an optical sensor called a bangmeter, an X-ray sensor, a dosimeter, and an electromagnetic pulse, EMP, sensor, W sensor, that form a major portion of the United States nuclear detonation detection system. General William Shelton has stated that future satellites may drop this feature to save money. While most clocks derive their time from Coordinated Universal Time, UTC, the atomic clocks on the satellites are set to GPS time. The difference is that GPS time is not corrected to match the rotation of the Earth, so it does not contain new leap seconds or other corrections that are periodically added to UTC. Following the United States deployment of GPS, other countries have also developed their own satellite navigation systems. These systems include the Russian Global Navigation Satellite System, GLONASS, was developed at the same time as GPS, but suffered from incomplete coverage of the globe until the mid-2000s. GLONASS reception in addition to GPS can be combined in a receiver, thereby allowing for additional satellites available to enable faster position fixes and improved accuracy, to within 2 meters, 6.6 feet. China's Beidou navigation satellite system began global services in 2018 and finished its full deployment in 2020. The Galileo navigation satellite system, a global system being developed by the European Union and other partner countries, began operation in 2016, and is expected to be fully deployed by 2020. Japan's Quasi-Zenith Satellite System, QZSS, is a GPS satellite-based augmentation system to enhance GPS's accuracy in Asia-Oceania, with satellite navigation independent of GPS scheduled for 2023. The Indian Regional Navigation Satellite System, deployed by India. Thank you for watching this video.